4.4 notes, Introduction to Related Rates. It says many variables have familiar relationships, or in other words, a way variables are related to each other. A great example is the Pythagorean theorem. So if you recall, that is a squared plus b squared equals c squared. It says, let's say a triangle's dimension are changing. This means a dimension A, B, or C has a rate of change, and this rate is related to another dimension's rate of change. Differentiate your relationship with respect to one specific variable. This is like implicit differentiation. Usually it is respect to time, but not always. So let's go ahead and take a squared plus b squared equals c squared and take the derivative respect to time. So what that means is we are going to take the derivative of each of these parts, and then we are going to write dA dt for respect to time for A, dB dt respect to time to B, and dC dt respect to time to C. So this would be 2A dA dt plus 2B dB dt is equal to 2C dC dt. Okay. In the first example, it says a police car is approaching a right-angled intersection from the north and is chasing a speeding car that has turned the corner and is now moving straight east. Set up a relationship, then find an equation that shows the related rates of the vehicles with respect to time. Well, let's say that here is the police car, here is the speeding car. We know this forms a right angle, which means we can label these sides and then solve using the Pythagorean theorem. And I use the word solve lightly. We're not solving for anything. We're putting it in terms of time and the related, the relationship sorry, I'm trying to make sure I'm using the exact words in here, the related relationship. So what that means is I do x squared plus y squared is equal to z squared. I do the same thing and take the derivative in respect to time. So I have 2x dx dt plus 2y dy dt is equal to 2z dz dt. Okay, we know that dx dt, we know that's in terms of x right here, and this is on the positive side, so this is going to be a positive rate. Okay, versus dy dt, this is the police car, right? Here's the police car going towards the speeding car, which means this y value is going to end up getting closer to the origin. So this dy dt is going to be a negative rate. Okay. And then let's look at what it would mean to have some rates that have constants in them. So it says an airplane, point A, is flying on a horizontal path that will take it directly over an observer, point O. The airplane maintains a constant altitude. Relate the rates of change in distance between the observer and the airplane and the horizontal distance between the two. Okay, so point A is the airplane. Okay, so here's my airplane. Okay. Point O is my observer. Okay, here's my person. And it's saying that it's flying a horizontal path directly above the observer. So I know it's going this way. Okay. The airplane remains at constant altitude. Fine. Okay. So since the airplane is flying this way, let's call this distance x. Okay. And we can end up connecting this to the observer. Let's make that y. And then the distance between them here will be z, which means we could do x squared plus y squared equals z squared. Take the derivative in respect to time, just like we did before. And so we get 2x dx dt plus 2y dy dt is equal to 2z dz dt. And here we see that dx dt dx dt right here is going a positive distance in relation to time. Dy dt is going to be constant because it said right here, the airplane maintains a constant altitude. So dy dt is going to be constant. Okay, and when we have something that's constant, okay, that means it could be any numerical value. Well, let's go ahead and make dy dt 0. And that way we're able to put it in terms of dx dt and dz dt. So set dy dt equal to 0, which implies we have 2x dx dt is equal to 2z dz dt. And these would be how the rates would be related. So dx dt related to dz dt. Okay, so for the practices, it wants you to set up a relationship using variables for the situation and then differentiate with respect to time t. Okay, so you're going to be doing the same thing that we did up here, but notice for these, a lot of them we use the Pythagorean theorem. For the other cases, that's not going to always be the case. So I'll do the very first example with you. It says an ice cube is melting. Relate the volume's rate of change with the edge's rate of change. So volume with the edge. Well, we know that a cube's volume is equal to the side cube. Okay, so side times side times side. So let's go ahead and take the derivative in respect to time. So that means I have dv dt is equal to 3s squared ds dt. And that's my answer. That's all it's looking for. So you're going to do that for every single problem.